So, today we will begin our discussion on semi-submersibles. Now, last class I have talked about FPSOs. Now, coming to the weather vaning aspect, I told you, but I could not find the L by B ratio. Now, you please remember one thing, that slender ships have good weather vaning characteristics. That is, L by B ratio is quite large. So, this is one characteristics with FPSOs we have to figure out. Weather vaning characteristics. Now, in this case, short bulky ships not desirable. Now, whenever you are designing ships, apart from your buoyancy and stability, the other point that is to be remembered is for FPSOs called weather vaning, that is your sea keeping characteristics, how it moves about your turret mooring, that is your surge, say, and yaw motions, and also the rotational motion. So, this you do not go for. Bulky means high displacement ships not having sufficient length. So, these will have more motions. So, do not go for that, but go for high L by B ratio ships. So, those are called slender ships. So, these are your FPSOs. Now, coming to today's discussion about semi-submersibles, which now they actually evolved from ships which are called submersibles. So, this I already told you. So, this was way back in 1947 in Louisiana. So, these submersibles were nothing but barge type hulls. This water depth was only 12 meters. So, semi-submersible actually evolved from the concept of submersibles. So, this was your upper deck which rested on columns which are supported by a mat. So, this is called a bottom mat. So, this was your wave and this was the seabed. So, this concept of semi-submersible was there in 1947 actually, before your oil exploration started in the 1970s. So, it was in this is 12 meters marshy land. So, this was called a bottom mat. This is essentially a pontoon hull, and this was your deck. Now, on this your drilling derrick etc. will be positioned. So, this is the deck. Sometimes this is called upper hull and lower hull. Now, this mat actually, if you take a plan view, it was in the form of a shape like this. So, at the middle you have a hole or an opening for passage of your conductor pipes, and most of the columns were located in this region. So, this was your mat. Now, this concept is still used in jack-up rigs. Jack-up actually there are two varieties you will find. One is called a mat supported type, the mat essentially looks like this, and the other is called the independent leg type. Anyway, So, these are coming to the semi-submersibles, which are floating platforms. They are actually deviations of this concept of submersibles, but submersibles you can understand they are only suitable for shallow waters. They can because of the small this length of column, it rested on this mat. So, this lower hull was flooded, ballasted, then it is then it rested in the sea bottom. But when you want to take this out, that means you have to deballast and also you have to loosen the mud around the mat. So, that is done by water jets. So, water jets will come around here and move the soil away, and then you can lift it. So, this was the concept. Now, what has happened in the deeper waters, this bottom mat was split in two. Now, when actually oil exploration started in deep waters, then the bottom mat was split into two pontoons. This was for the sake of transit, for easy transit. So, this was how the evolution took place for the semi-submersible. Now, coming to the semi-submersibles, there are certain factors which are very crucial. Now, so this actually evolved around this is called first generation design, first generation, then you have second generation, then third generation, and now we are in the fourth generation. So, the design has evolved over these phases. So, this was prior to 1971, then this is 1971 to 1980, and 1981, 1984, and this is 1984 and beyond. So, this is 1998, and still I think no further development has taken place out here. So, this is how the thing has evolved, and coming to the configurations, you will find the first generation actually looks somewhat like this. So, these are your pontoons, then this was your deck and columns. Now, with greater amount of knowledge about waves and all this, so this also started here, and these are called horizontal braces. These are called brace. And then second generation, you can see the pontoon was cylindrical in shape. So, now actually this has evolved into a rectangular hull with bracing, cross bracings. So, this is your space frame construction. So, second generation. Now, here you can see that the deck is a truss type of deck. Basically, it is resting on this three-dimensional truss. Pontoon, instead of having circular cross section, it has become rectangular. Now, this has further evolved actually into this type of structure. Now, here you can see that the columns, size of columns has increased. Now, with more and more knowledge about wave forces coming into the design phase, you find that this was the evolution. One thing you should note that now the deck of the platform has increased in size. So, here now instead of having so many bracings, the bracings have been reduced in number, but still we have the rectangular hull type of pontoon. So, this is another configuration. Now, this system you find that bracings are like this. So, instead of having, so these are the critical joints, this one joint, another joint, there are so many joints. Now, joints are actually hotspot regions. So, these are actually likely spots for cracks, development of cracks and ultimate failure of columns. So, here you can see the design has taken place in such a manner as the joints have been reduced, and here instead of having a truss deck, so this is called open deck, and this one is called integrated deck. So, bracings have been reduced, column diameter has increased from the first category, and the fourth. So, this is your third generation, and fourth generation has totally dispensed with your bracings. So, this is called the fourth generation, but column diameter is more or less the same, and you have the integrated deck, but you have done away with the cross bracings. So, this is another variety. Instead of, you can only have only one horizontal bracing. So, I told you bracings are actually likely spots for failure or stress concentrations. Now, nowadays you have various configurations of this category. So, this is your fourth generation. So, yeah, actually this is the evolution of the semi-submersibles. So, no cross bracings, just only one tie bracing between the columns. So, evolution has taken place, and now what we have to study is in the design. See, semi-submersibles, what is the performance or performance requirement? Now, I will give you more variations of the fourth generation. So, what you have seen is only the one type. Now, performance requirement or the work requirement of semi-submersibles can be number of types. Now, it can be employed as an FPS or a floating production system. Now, it can be employed as only a drilling platform. So, these are the many aspects of functions of a semi-submersible. Number 3, it can also act as a pipe laying platform. So, these are the major uses of semi-submersibles. Pipe laying platform, that is the offshore pipelines. So, those are actually assembled on semi-submersibles because they have a large deck area. Okay. So, drilling, floating platform, what else? Number 1, it can also act as space launch platform. So, that means missiles etc., or launch vehicles can also be from semi-submersible. So, these are some of the many uses. Now, accordingly, there are two types semi-submersible. When you go for semi-submersible design, now you have to figure out whether this is stationary at one place or it can go for transit. So, these are the two variants in the design. First is stationary at one place, and the other is frequent transit. So, which one we will go for? So, that depends on the job requirement of the semi-submersible. Okay. So, there one design will pertain to this. Now, stationary at one place, that means here you do not require any reduction in the resistance of the platform. Resistance is not the major criteria. Your major criteria in this case will be motion limitation. Now, frequent transit, that means here actually you should have short transit time. So, this should have less resistance or good, that means you write minimum resistance. Motion is secondary, and of course, less motions. So, these are some of the variants. You have to decide on which category the semi-submersible will fall according to the job requirement or work requirement. So, based on that you have to do the hull form design. So, hull form design is actually centered around these specific requirements. So, based on this, the moorings. So, here actually moorings for long term application. And for this short term mooring design. Now, what is this long term and short term? So, that means in your mooring analysis, you have to do you have to calculate the motions of the submersible. So, here actually you go for 100-year storm criteria is better, and here you go for lesser amount of time, say 25-year maximum wave height, significant wave, 25-year storm. So, this is how the thing actually goes. Now, suppose that is when the motions are very unfavorable. So, you should have quick transit. So, that means you have to run away from the place of the hurricane, say Gulf of Mexico, that means you are getting the hurricane is coming. So, that means you have to quickly unhook your tethers or unhook moorings. So, that is called quick connect disconnect of moorings. So, these are some of the this thing design variations in the design. So, here actually you should do long term wave analysis, and here short term wave periods, quick connect disconnect mooring and minimum resistance. So, actually all these things are carried out in what is called a sea keeping basin for tank. So, either this you have to find out normally from calculation of vessel rows. So, here actually in our department we do not do this, but this is a very important area of study. So, this semi-submersibles you go for, this is sea keeping tank experiments. So, IIT Madras does this. So, here you calculate the response of the semi-submersible with waves. Now, anyway, so now coming to the design phase, semi-design. Semi-submersible, there are various aspects of this. First one, you figure out weights. You calculate weights, LCG, VCG, etc. So, weight summary is very important. Now, you calculate hydrostatics. So, this actually we have to do, you have to find out what is called your design spiral. I have already talked about. So, you start from the owner's requirement and go for final design, and these are the various spokes, weights, LCG and all this. You go for number of iterations and make the design much more refined. Calculate tank capacities. Then 4 is intact stability. So, these are some of the naval architectural considerations. What else? Calculate damage stability. So, all this you have to do. Then wind forces. Of course, if you want to find out damage stability, I think probably this you have to do first. This is wind forces. Then current forces. Current forces are required because the semi-submersible is moved at one place. Ballast. Then sea motions. And number 10 is find out global strength. And last one is fatigue. So, these are the some of the steps you have to do in following semi-submersible design. So, 9, 10, 11. Now, operating conditions. Constraints in design. So, you formulate your design spiral with those spokes which I have already talked. Where is that? Now, what are the constraints? Now, you cannot keep on increasing the dimensions as you like. So, first one is maximum light ship draft. So, from where this you find out this? This you can do from quay side or quay side outfitting. So, outfitting is normally done on the quay next to the shipyard. So, what is the draft over there? So, that means the semi-submersible should have a large draft for outfitting on the dock side. So, from this you calculate draft. Next, how do you find out the maximum beam? Now, this you find out from canal width, canal stroke dock width. The other one is dry transportation. So, what is this dry transportation? Now, dry transportation means the whole semi-submersible is transported on a supply vessel. So, semi-submersibles are not very friendly towards the resistance part or tow. It is not tow friendly. So, that means you have to load the semi-submersible on a barge or offshore supply vessel and take it to the site. So, that is called dry transportation. Now, whether you are having sufficient beam or very large beam for dry transportation. So, the semi-submersible is literally carried on top of a say offshore supply vessel or a barge like this. So, your semi-submersible will be somewhere here position. Now, you have to calculate the stability of the barge with semi-submersible on the deck. This is how it is carried. So, this is like your I told you like you carry transport jacket on top of a barge. So, this is semi-submersible carried on top of it. So, this is dry transportation. So, maximum beam you find out, maximum light ship weight. Now, in this case you cannot increase the size of the semi-submersible or the weight of the semi-submersible, because you will sink the barge, isn't it? Sink or capsize the barge. So, there is a maximum light ship weight. Light ship weight with what? With VCG. So, this you have to calculate for dry transportation. So, this you have to figure out. Then environmental criteria. Now, semi-submersible there will be actually 3 or 4 operating modes. One is the operation, that is either in the production or drilling. Number 2, you will have transit, and 3 is survival, storm survival. The other one can be installation. Now, ships actually you have calculated your GZ or GM for how many loading conditions? Basically, you have calculated for 2 loading conditions, isn't it? The light ship and loaded departure or light ship arrival, whatever. See, semi-submersible will ask you for all this. So, you have to calculate your GZ curve for all these conditions. So, all these conditions we have different drafts with different GM and GZ values and different heaving arms and all that. So, these you have to give it to the approving authorities, say ABS, then IRS and all that. They will ask for this document. So, you can see for offshore, if you go, the criteria is much more rigorous. Anyway, so these are the loading conditions, and here these loading conditions will give you. Now, this kind of offshore structures, now ships basically you will find they are what? That means the weights are the weight configuration of ship is symmetrical about center line, more or less. Have you seen? Ships are actually about the center line, the hull form is similar, and also the weight distribution is symmetrical about the center line. That is, normally you calculate the weight about, you make the LCG and VCG, and that is the what you have done the calculation only for that. So, the LCG is important because of trim. Now, in case of this type of ships which have the breadth is quite large, you also have to do the transverse center of gravity, but in this case you will have to find out what is called eccentricity of deck load. Now, your weight distribution on the deck may not be, it is evidently it is never symmetrical. So, this is called eccentricity of deck load. So, that means at one end you will have a crane. The crane say will weigh something like few hundred tons. So, for this you have to do what? In order to counter this, you have to always do trim and heel calculations for different disposition of the deck load. So, that is called deck load eccentricity. So, this will give you adverse trimming and heeling moment. So, this has to be countered by, that is why you require what is called ballast, and ballasting of what? Corner columns. So, at the corner of the columns you will find large ballast tanks. So, essentially these are called trim tanks. So, this is the job. So, anyway, so that is lateral eccentricity. Now, calculate this is 3 environmental conditions, 4. So, this is 5, 6 is motions. So, motions are actually very important for this type of ships, more than your say cargo ship or passenger ship, because of the reason of riser breakdown or riser breakup, conductor pipes snap. So, all related to motions. Now, motions calculation you have to do from environmental loads and accelerations. So, basically you have to calculate the accelerations from environmental load. So, this is the aspect, and then the last one is of course applicable rules. Now, whatever you have to do, you have to conform to say ABS or DNV. So, these are some of the rules. So, these have to be followed. The other one is API, American Petroleum Institute. So, based on this, the semi-submersible has to be configured, that is your hull form, hull shape configuration. Or rather hull form design you can write after you have done all this study. Now, this if you want, it boils down to number A is stability to payload. Now, this is another very important criteria in your hull form design, that is the lifespan that you will be drawing. That is basically you have to figure the column height and the length and breadth depth of the pontoons. So, you have to keep the deck always above the highest waves, otherwise you will find that your deck is going to be wet all the time. And not only that, wave impact. Wave impact on deck. So, this can play havoc to your say production and drilling operations. So, this is essentially done by calculate air gap, or you find out minimum air gap requirement. This is very crucial, because otherwise your deck is going to become wet and you will have lot of wave impact loads coming on the say quarters, living quarters, drilling derrick and all that. So, that because your major operation is on the deck. So, the crew and all that will be operating the various valves, pipelines etc., on the deck, BOP and all that, and they will get washed away. So, this is minimum air gap requirement is a fundamental criteria of design. Now, next you have, so this of course, the other smaller item is wave run up. On columns. So, this is called wetness. So, the wave comes and impacts the columns, then it goes away, but your column is going to be wet, is not it? So, that is also to some extent, I mean this is a minor issue where you have to do all the painting, corrosion protection because of this. So, that is called wave run up on columns and wave impact. So, you study, so these are very crucial, wave impact, wave run up. So, a lot of hydrodynamics is involved at the free surface. So, response to waves. So, this is one of the guiding lines for form description. Now, form basically you have to split up hull form into 4 categories. Now, in ships what you do? Ships is just one single volume, isn't it? Normally you fix up your length between the perpendiculars and then your breadth, molded depth, block coefficient, draft, finish. But here actually you have to do independent design of, first you do for pontoons, next you do for columns, next number 3 is deck, last one is what? Space frame. So, actually the work is more from your ship design, because you have to independently design all these 4 categories. So, I will give you one of the descriptions. Pontoons, what is the configuration of your pontoon? There are various types of pontoons. First 2 types I have told you, one is cylindrical, the other is squares shaped with rectangles and all these things. Next you can have a ring type of pontoon. I will show you some of the designs. Now, columns actually, pontoons you fix up size and shape. Columns, length and diameter. Deck depends on what? Now, either you have to go from deck to columns or columns to deck. Now, deck area, you have to find out area number. You can have more than one deck, and this will depend on column spacing. Space frame, of course, this will depend on column spacing. and rigidity. Now, this you have to calculate from structural, what is the rigidity of the structure or the stiffness of, basically you have to calculate truss stiffness. In finite element method that we are studying this, you have to calculate the stiffness matrix. Now, this you have to do both for static as well as dynamic case. Now, static analysis you get the static forces, and dynamics you calculate omega and omega bar. That is the wave frequency and the response frequency. So, remember this type of platforms you always keep it out of the resonant frequency range, semi-submersible or TLP, very very crucial, otherwise it will be a disaster for marine riser. And mooring, the first thing is, in case of resonance what will occur, I am telling you. If this is the situation of omega equals to omega bar, immediately you will have riser snap. This is quite dangerous, and you can have mooring line snap. Your structure as a whole will remain as it is, but these two will go. So, in order to prevent this, very accurate calculations have to be done for dynamic analysis, this omega and omega bar. Find out the natural frequency from your eigenvalue calculation and also your resonant, the wave frequency. So, anyway, so these are some of the hull form design. So, here you can see the design is more complex than that of a ship. Now, basically here these pontoons column, the space frame and the deck is actually area based. Now, area based, actually you have to figure out what are the type of equipments, weight, their weight configuration, LCG, VCG and all that. So, those data will define your deck. Now, columns, actually you will find, so your semi-submersible is called a, sometimes they are also called column stabilized platform. You will come across this in the literature. Now, what is the meaning of column stabilization? Now, from the structural engineering concept, this is called structural stability. Structural stability is, that means it will not buckle. Basically, buckling, this the failure against buckling is called the column stability. But in this case, column stability actually means your that naval architectural stability. This should give good static and dynamic stability. From what? From waves. So, columns are essentially the volume which gives you static and dynamic stability, because your pontoons are way below the water surface. So, pontoons are not in the operating mode. So, there are actually a number of modes. In the transit mode, actually the columns are, so in transit mode what happens, columns are above the water surface, sorry, not columns, pontoons above water surface. Now, in this case you are getting very high water plane area. Now, this is a case of high water plane area, good for stability, but at the same time you have high CG, which is detrimental to your GM, isn't it? So, everywhere you have to do all this calculation of CG, high water plane area. So, high water plane area, this is good for your BM. BM is equals to I by V. So, you have to find out this moment of inertia of the columns, which is giving you BM, and here you calculate your VCG. From this you calculate GM. GM calculations are very crucial. So, this is in transit mode. Now, in the operating mode, now here actually the semi-submersible floats on, these pontoons are immersed or submerged, you can say. Now, so here this is actually, it entails loss of water plane area. So, water plane area is lost. So, this will reduce your BM. So, at the same time, but your because your G will go down because probably you have ballasted, isn't it? So, this you have to find out GM in both categories, operating mode as well as transit mode. So, you have to decide, the hull form design is basically centered around your stability calculations and your space frame. Now, your structure, that is the strength and stiffness. Coming to the structural aspect, strength and stiffness. So, these are normally given by, this comes from major strength part is your pontoons. Pontoons, bracings of the truss or rather you write truss bracings. And last is your columns. So, structure if you want to calculate, first you calculate from pontoons, truss bracings and then columns. These are three main structural items. From this you calculate your this stiffness K matrix. So, this you have to decide from the structure point of view. The draft has there are two modes of this draft, that is transit and operating mode, and calculation of internal volume. Internal volume of columns, pontoons. Now, how do you calculate this? Now, columns actually storage for anchor chains. So, your semi-submersible will have huge anchor chains, say a few kilometers long. So, those have to be hauled up by means of winches and stored in the columns. So, column has to have sufficient volume to accommodate anchor chains. Next, ballast water. Ballast water can be in columns. Corner columns are provided with ballast water for trimming, eccentric load coming from cranes and other deck load. So, those you have to trim by means of varying the ballast water in the corner columns. What else? Pump room. Columns may have pumps, machinery. So, all these require space, volume. So, you have to provide all this volume inside the columns. The length of column is dictated by what? Your air gap, mainly your air gap requirement, and your draft. Draft is again a crucial issue for deciding the length of columns. Now, pontoons also same thing will come. Now, pontoons, do you have ballast water? but pontoons you do not store chains. Mainly pontoons have ballast water pump rooms. Then you may have what else? Ballast water pump rooms. Then you may have this machinery rooms. Sorry. Machinery for thrusters. So, pontoons are normally provided with bow and stern thrusters in case of semi-submersibles, because in order to change the orientation or station keeping. Machinery for thrusters, these are required for station keeping. Now, some of these semi-submersibles may be provided with their own propelling machinery. So, these are to be housed inside the pontoons. So, you have to give sufficient volume and space for all this. Fuel oil tanks. If you have machinery, you will have fuel oil tanks. Columns can also act as cargo storage if it is found necessary. Cargo oil storage tanks. So, this is the volume calculation of your semi-submersible. So, you have to calculate all these tank capacities, you calculate volume of all the machinery, anchor chain, all these requirements will be there. So, this is you find out columns, pontoons columns, and then your space frame is normally your this thing, giving the stiffness to the structure. And all this is actually, all this paraphernalia is from the support to the deck. So, deck support is coming from the underwater part. Next is the motion calculations, and you calculate the mooring. So, you have to calculate, basically find out semi-submersible displacement after you find out all the weights. Weight breakup, I think I have given you, no? Yeah, weight breakup, some weight breakup I have given. From this calculate displacement. Now, so how do you start your design? Now, semi-submersible design, you follow the principles of your ship design. This you start from similar semi-submersibles. In similar environmental conditions. Now, this is very important. So, with that is the starting point of your design spiral. Now, each site will have its own environmental will be different. So, that has to fine tuning the design. So, keep on changing the parameters till you come at the converge of the correct pattern. So basically